So what's the state of our energy grid, Adi?
So when you come to the grid, there are two pieces. There's the big grid, which we call the transmission grid, and then the get it to people grid, which is called the distribution grid.
Mm-hmm.
And the transmission grid is the biggest single machine in the Southern Hemisphere. It is also the most complex single machine in the Southern Hemisphere.
Oh.
Very few people know this. It starts right up at the top of Queensland, and it goes all the way down to Port Augusta in South Australia. It is a long string with some side branches taking electricity from all the existing power plants, of which there are a number at the top of Queensland, and there are a couple in South Australia. They've shut most of them down. And of course, they're in New South Wales and Victoria as well, and Tasmania has got the hydro. So essentially, this grid, this massively complex machine, is used to safely transmit electricity to literally most of the population on the East Coast in a reliable, productive way at low cost.
Okay, East Coast.
On the East Coast. There is a West Coast grid as well, which is a smaller grid and runs on similar principles. But the thing to remember about the grid, which people don't understand, is that the electrons at the top of the grid and the electrons at the end of the grid are exactly at the same second of time at 50 hertz in a beautiful sine wave that is right across that whole stretch of that whole distance. Right. And it's not just an electricity transmission device, it's a timing device. So many industries use the grid to time critical processes, because if you know that you're on the same cycle at the top of the grid and the same cycle at the bottom of the grid, and you want to send a message to somebody, you can use the grid. So you can use it for communication. You can use it for sequencing critical processes where something's happening in one place and another thing must happen in a different place. Right. So if you're coordinating, for example, deciding how to move goods around in a distribution system, it's a lot cheaper than setting up a communication system to use the timing device on the grid to set up your communications. People don't understand the value of having a timing device that is accurate to less than a 50th of a second. It's like a beautiful stopwatch that you can have available all of the time. Not only that, but you can use that wonderful frequency control in order to check when there's too much power being sucked out of a part of the grid and another part of the grid, because it slightly modifies that frequency above and below 50 hertz. So when there's a lot of power being drawn out of the grid, the power drops. When there's a little bit too much on the grid, the frequency drops or the frequency goes up. Right. And so your power management in the grid can be articulated through the frequency control in different parts of the grid. You can find out really who's doing the heavy lifting in the grid at any time and who's not doing enough. And that allows communication between the people who are driving the electrons through the grid to synchronize the machines that they've got to get them absolutely optimal. So this is a remarkable end-to-end device that it is not just providing electrons, but is providing synchronization, it's providing timing services, it's providing communications, it's providing a whole range of things. And that benefit is increasingly being lost because as we take the big assets out of the grid that are currently producing the electricity, we lose the benefit of those signals. Because when you've got a wind turbine farm, all of those are spinning. They spinning at slightly different speeds because the wind speeds are different at different parts of the wind turbine blades and at different wind turbines across the site. So you gather all of the DC direct current that's coming out of that. And at the fence, you have a thing called a digital inverter. Right. And the key word is digital. It's a box of electronics. So it sniffs what's happening on the grid, and then it tries to synchronize all of the slightly different signals coming from the other ones and convert that into a 50 hertz signal that goes onto the grid. It's what I call messy 50 hertz because it isn't timed. There is no inertia. It's floppy. And as you add more wind and solar to the grid, your grid gets floppier and floppier and floppier. That means that if you don't have resilience in your grid and you don't have a beautiful timing signal, you lose industries. We have already lost industries from South Australia. They didn't stop in Victoria. They didn't stop in New South Wales. They didn't stop in Queensland. They are now on the west coast of the United States.